All right, welcome everybody. Today we're going to talk about lesson number 51, and this is a lesson about harmonic motion and trig graph applications. Now, harmonic motion is a physics topic, so again, depending on your familiarity with physics concepts, it may or may not be familiar. The good thing about harmonic motion is that it's known to be simple, so we're really only going to be talking about changes to A, B, or a negative out front. It does not involve any changes to D, at least not as of yet. So even though technically this is new, it fits right in with the graphing changes we've been doing so far. So let me kind of set the scene for you a little bit. When you're talking about where you would use harmonic motion and where you would use trig graphs in particular, because of the periodic nature of trig functions, which of course means that they repeat, you would basically want to use it anytime you have an object that is either vibrating, oscillating, rotating, or being moved by some kind of wave motion. So kind of the easiest way to set the scene here is suppose that you have a ball that is bobbing up and down on the end of a spring. So suppose that 10 centimeters is the maximum distance that the ball can move vertically or downward from its equilibrium, which is the position at rest. Where the problem is starting, whether it's starting at 0, 0 or some other value, is one of the most important factors in determining whether you're going to use a sine or a cosine. So again, a very important fact. They're telling you further that the time it takes for the ball to move from its maximum displacement above 0 to the maximum displacement below 0 is going to take a total of 4 seconds. We're going to make a couple of assumptions here. This is kind of what keeps it simple. And we're assuming that there is perfect elasticity and no friction or air resistance, which means that the ball would continue to move in the same fashion no matter what. So just by reading that and just by looking at the picture, there actually is a fair amount of information that you know. So I want to make sure that you know it. So first and foremost, the fact that you are starting at 0 centimeters for displacement at the point of equilibrium, that tells you something important. That is telling you that the displacement is equal to 0, and that is telling you that the time is equal to 0. So since time, comma, displacement is equal to 0, 0, there's only one wave, the sine or the cosine, that goes through the point 0, 0, and hopefully you remember that it's the sine wave. So again, where you're starting at rest is important in determining whether it's the sine or the cosine. And again, because it goes 0, 0, goes through 0, 0, that's how we know that it's the sine. So further, there is more information. The fact that it takes exactly 4 seconds to go from its maximum displacement to its lowest displacement or its minimum displacement, that is going to be the period. So the period is going to be 4 seconds. What does the 10 mean? Well, the fact that you are going 10 centimeters above rest and then 10 centimeters below rest, that is going to actually tell us the amplitude. And then new for this section so far, but there is also something we can determine, which is called the frequency. The frequency is the number of cycles per second. And in this case, the frequency is 1/4 cycles per second. If you're wondering, does that 1/4 have anything to do with the period? It does, which we're going to see in a second. So again, so far, we know that we're using the sine function because it goes through 0, 0. We've just discovered we know the period, we know the amplitude, and we know the frequency. So before we go ahead and actually write an equation, let's go ahead and take a look at the rules. And again, these are going to be the rules for something called simple harmonic motion. And again, simple harmonic motion means only changes in A, what would be the B, or orientation. So again, simple harmonic motion, you are going to use the following two models. D equals A times the sine of what looks like a WT, or D equals A times the cosine of what looks like WT. So notice that there are slightly different letters here. The D, of course, stands for displacement, A stands for amplitude, T stands for time, and then that weird W looking thing, to be honest, I looked up how you say it for the Greek alphabet, and I really can't even pronounce it. So I'm just going to go ahead and call it the W, since I really don't know how to say that word. What it actually means is it means the stiffness of the spring, how readily it's able to bounce up and down. So that's what it means in the context. So those values, how are we going to use those and apply to what we already know about trig functions? Well, the amplitude is always going to be the absolute value. The period, instead of being 2 pi over b, it's going to be 2 pi over that w, just because that is the variable that they use. And then notice that the frequency is the reciprocal of the period. So you can either think of it as being the reciprocal, or you can understand that the frequency is equal to 1 over the period. So you're going to use whichever of those two interpretations is easier. So again, both of these mean the frequency. It's either the w over 2 pi or it's 1 over the period. So again, use whichever one makes more sense to you. So we're now going to go ahead and write the equation for the ball that was up above. So again, because of the fact that we know that it goes through 0, 0, we know that it has to be a sine wave. So we know that it's going to be d equals a times the sine of wt. The amplitude, again, in this case, they're using little a, and that is always going to be a absolute value. So that would be the absolute value of 10, which would be 10. Then we know that the period is equal to 2 pi over w. And because of the fact that it took exactly 4 seconds to go through the entire motion, we're going to go ahead and set that equal to 4. Cross multiply, so 2 pi equals 4w. W equals 2 pi over 4, which is going to be pi over 2. So from here, we now have everything that we need to write our equation. So d for displacement is equal to, the amplitude is 10. We know that it's a sine. We know that w is pi over 2 times t. So that is my equation that represents the spring in question. Then one final question here. What is the frequency of the harmonic motion? So again, there are more than one way that you could answer that question. The easiest of which is the fact that it is 1 over the period. So the frequency, which we'll say f, is equal to 1 over the period, which means that the frequency is equal to 1/4. So both of those things highlighted in green are the two things we needed to know. And the truth is, solving for this equation was pretty much exactly the same as all the solving that we've done so far. You're just using different letters, and then they actually mean something in the context of the problem. So let's go ahead and try something similar here for number 2. So again, find the model for the simple harmonic motion under the following conditions. So the most important thing here is the fact that it's 0, 0. If it's 0, 0, we know for a fact that it has to be a sine wave. The fact that the amplitude is equal to 4, we know that's A. The fact that the period is equal to 6, we're allowed to then, because the period is 6, we're going to set that equal to 2 pi over w. Technically, it's 2 pi over b, but again, they're using w as their variable, so I don't really care what variable you use as long as you can get to the answer. So 6w equals 2 pi. So w equals 2 pi over 6, which of course becomes pi over 3. So if you put all that information together to get the answer, you're going to say the displacement is equal to 4 times the sine of pi over 3 times t. Again, it does get harder, but not so much for today. We're really focusing again on simple harmonic motion. So let's go ahead now and take a look at 3. Again, simple harmonic motion, they're asking you for the same thing, but really the only difference here, but it's an important one, is the fact that you're saying that you're starting at 0, 2. The fact that you're starting at 0, 2 is how you know this has to be a cosine problem as opposed to being a sine problem. So if it starts at anything other than 0, 0, it has to be a cosine. This displacement and this amplitude have to be equal, or else the problem wouldn't make sense. Also for period, please make sure you know 3/2 is equivalent to 7 over 2. It just helps us keep it as a fraction. So again, if the period is 7 pi over 2, then 2 pi over w is going to be equal to 7 over 2. So cross multiply, 4 pi is equal to 7w, which means that w equals 4 pi over 7. So putting that all together for my equation, d for displacement is equal to 2 is the amplitude times the cosine of 4 pi over 7, and then don't forget the t. So finding equations either from some situation like the first one or from some table data like number 2 and 3, that's what you should be able to do so far. And then now suppose that I have given you the equation and I've asked you to go ahead and solve. So now you're kind of working backwards. So given the simple harmonic equation, d equals 6 times the cosine of 3 pi over 4t, you're going to go ahead and be asked to find the following. So if they're asking you for the maximum displacement has to be the amplitude, which in this case is going to be 6. In order to find the frequency, remember that in some of the examples so far, we've done 1 over the period, but in this case, we don't actually know the period. So instead of using that descriptor, we're going to use W over 2 pi. Remember, if you go back to the other side, there are 2 different ways to think about frequency, depending on what information you're given. And in this case, the fact that you're given W over 2 pi, or because you're not given the period, this is the one we want to use. So W divided by 2 pi, that's going to be 3 pi over 4 divided by 2 pi over 1. So we're, of course, going to multiply by the reciprocal. So 3 pi over 4 times 1 over 2 pi. We're going to then go ahead and cancel the pi's, and you're going to get 3 over 8. Here's what it actually means in terms of frequency. It means that there are 3/8 of a cycle per time unit. So whatever it happened to be, minutes, seconds, hours, whatever it happened to be, it's going to go through 3/8 of a cycle for every 1 hour, minute, or second. To find the value of d when t is equal to 4, that simply means you're going to plug a 4 in for t. So d is equal to 6 times the cosine of 3 pi over 4 times 4. That's going to tell you that d is equal to 6 times the cosine of 3 pi. Go ahead and get a little bit more room. The cosine of 3 pi, you would have to realize that starting at 0 pi, this is 1 pi, then this is 2 pi, and then 3 pi would leave you back here. That's the point -1 comma 0. The cosine is the x value, so that would be 6 times -1, which means that the displacement would be -6. Just highlight a couple of these things for you. Just a note for C. For C, you could use the calculator, but you would have to make sure that you're in radian mode if you were going to do so. Okay, and then as far as D goes, we're actually going to skip D. It's a fine question, but it's very nuanced. The truth is, you probably would never be asked this anywhere else, and you probably would never remember it anyway. So we're just going to go ahead and skip D. So let's go ahead and try 5, which is a very similar scenario here. So given this harmonic motion equation, we're going to go ahead and be asked to find the following. And obviously, it should get easier the more you do of these. So the maximum displacement with very little work, you should hopefully understand that that is the amplitude, which is, of course, going to be 4. Again, in terms of the frequency, because you don't know the period, you're better off using the definition of W over 2 pi. So in this case, that would be 6 pi divided by 2 pi, which would be 3. And again, what does that actually mean? It means that there are 3 cycles per time unit. Even if you just say 3, that's fine, but I want you to understand what it is you're finding. The frequency is how many cycles are going to occur for any 1 unit of time. Find the value of d when t is equal to 4. So that means you're looking for the value of 4 times the cosine of 6 pi times 4. That means you're looking for 4 times the cosine of 24 pi. Again, if you're going to use a calculator, you have to make sure you're in radian mode. Otherwise, hopefully you know that 24 pi is coterminal with 0 or 2 pi. So this is the point 1 comma 0. The cosine is the x value, which is 1. So this would be 4 times 1, which means you are going to get a value of d equals 4. And just like the previous problem, while D is a fine question, we really don't need it. So we're going to go ahead and skip that. One final question about harmonic motion here for today. A point on the end of a tuning fork moves in a simple harmonic motion described by the following. So here they're telling you to use a sine wave. Find the W, which again means the stiffness, given that the tuning fork for middle C, and that's just a specific tuning fork, has a frequency of 264 vibrations per second. So first off, you have to remember that the formula for frequency is W over 2 pi. Because they're telling you that the frequency is 264, you're going to go ahead and set that equal to W over 2 pi. You're going to go ahead and cross multiply, which means that the W in this equation is equal to 528 pi. And I don't know if you've ever seen a tuning fork or if you have any kind of, music background or whatever, but they really do vibrate, very quickly. So that's why you're going to go ahead and get that W. So just something to keep in mind. So we'll go ahead and pick up the second part of the lesson in part B of lesson 51. But for now, thanks very much for tuning in, and we will catch you next time.